Imagine standing at the edge of the universe, peering into the infinite darkness, your hand outstretched toward distant galaxies that shimmer like diamonds scattered across velvet. You want to reach them. Every fiber of your being yearns to touch those distant suns, to walk on alien shores, to bridge the cosmic gulf that separates us from the rest of creation. But here's the devastating truth that science whispers in our ears, a truth so profound it reshapes everything we thought we knew about our place in the cosmos: we will never, ever travel at the speed of light. Never. Not because we lack the imagination. Not because we haven't tried hard enough. Not because the right technology hasn't been invented yet. But because the universe itself, in its deepest architecture, in the very fabric of reality, forbids it. The speed of light isn't just a speed limit. It's a cosmic commandment written into the foundation of existence itself. Think about that for a moment. Really think about it. We stand on this tiny world, gazing up at stars that have called to us since the first human looked skyward and wondered. We've built telescopes that can see to the edge of the observable universe. We've split atoms and mapped genomes and sent machines to other worlds. We've conquered so much. Yet the one thing that would truly liberate us, that would transform us from planetary children into genuine citizens of the galaxy, remains forever out of reach. Why? What is it about light speed that makes it so absolutely, utterly, completely impossible to achieve? The answer lies in something so strange, so counterintuitive, so alien to our everyday experience that even after more than a century of confirmation, it still feels like a cosmic joke. The universe doesn't work the way we think it does. Space and time, those fundamental backdrops against which all of existence plays out, are not what they seem. They bend. They warp. They twist and merge and transform in ways that shatter our common-sense understanding of reality. For thousands of years, humanity operated under a beautiful, simple, and completely wrong assumption about the universe. We thought space was a stage, unchanging and absolute. We thought time was a river, flowing steadily forward at the same rate for everyone, everywhere. We thought that if you could just build a fast enough ship, add powerful enough engines, generate enough thrust, you could go as fast as you wanted. Speed, we believed, was simply a matter of force and engineering. Want to go faster? Apply more force. It seemed so obvious, so natural, so right. This was the universe of Isaac Newton, a clockwork cosmos operating according to elegant, predictable laws. In Newton's universe, space was a container that held everything. Time was the universal ticker that measured all change. Matter was stuff that filled space and moved through time. And motion? Motion was beautifully straightforward. An object at rest stays at rest. An object in motion stays in motion unless acted upon by an outside force. Want to accelerate? Apply a force. Want to go twice as fast? Apply twice the force, or apply the same force for twice as long. There seemed to be no theoretical limit, no cosmic speed trap, no fundamental barrier to how fast something could go. Picture a ship sailing across an infinite ocean. The ocean doesn't care how fast the ship goes. The water doesn't suddenly become thicker, more resistant, more viscous as you approach some arbitrary speed. In Newton's universe, space was like that ocean, neutral and indifferent to your velocity. You could, in principle, just keep accelerating forever. You could reach any speed you wanted, given enough time and enough fuel. The speed of light? Just another speed, nothing special, nothing sacred. If light traveled at a certain speed, well, that was just how fast light happened to move. Build a better ship, and you could overtake it. This understanding shaped everything. It made sense of our world. It predicted the motion of planets and the arc of cannonballs. It built bridges and guided ships. For centuries, it seemed like humanity had figured out the fundamental rules of the game. We understood motion. We understood the universe. Or so we thought. But then came the experiments. Oh, those maddening, impossible, reality-shattering experiments. In the late 19th century, scientists started trying to measure something that should have been straightforward: the speed of light. They expected to find that light, like everything else, moved differently depending on your motion. After all, if you're on a train moving forward and you throw a ball forward, the ball's speed relative to the ground is your speed plus the ball's speed. That's just common sense. So if Earth is moving through space, and light is traveling through space, then light should move faster in one direction than another depending on Earth's motion through whatever medium light travels through. Except it didn't. The experiments, performed over and over, with increasing precision, kept giving the same impossible result: light always moved at the same speed. Always. No matter which direction you measured it. No matter how fast you were moving. No matter what time of year it was, even though Earth's orbital motion changed dramatically. Light speed was constant. Invariant. Unchanging. This made no sense. None. It violated everything we thought we knew about motion and velocity. Imagine you're in a car driving down a highway at 60 miles per hour, and another car passes you going 70. From your perspective, that car appears to be moving at 10 miles per hour relative to you. That's how relative motion works. Now imagine that instead of a car passing you, a beam of light passes you. According to everything humanity had learned about motion, if you measured that light speed while moving, you should get a different number than if you measured it while standing still. But you don't. You get exactly the same number. Every single time. What could this possibly mean? How could the universe work this way? Scientists were baffled, disturbed, forced to question everything they thought they understood. Some suggested there must be experimental errors. Others proposed that perhaps Earth dragged something called the luminiferous ether along with it, masking the expected effect. But the experiments were rigorous, and the results were clear. Something was deeply, fundamentally wrong with our understanding of reality. Then came a patent clerk in Switzerland. A young man with wild hair and wilder ideas, someone willing to question the unquestionable, to doubt the obvious, to rebuild physics from the ground up. Albert Einstein looked at those impossible experimental results and made a leap that changed everything. He asked a simple question: what if the experimental results aren't wrong? What if light really does move at the same speed for everyone, no matter how fast they're moving? What would that mean for our understanding of space and time? The answer was revolutionary. If light speed is constant for all observers, then space and time cannot be constant. They must change, must transform, must be flexible and relative depending on how you're moving. Space and time, Einstein realized, are not separate things at all. They're woven together into a single fabric, a four-dimensional tapestry called spacetime. And motion through space is intimately, inescapably connected to motion through time. Think of it this way. Imagine you're walking across a field, and you can walk in any direction you choose. If you walk straight north, all your motion is in the north direction. But if you walk northeast, your motion is split between north and east. The faster you move east, the less of your motion is available for moving north. Your total speed stays the same, but how that speed is divided between different directions changes depending on which way you're heading. Spacetime works similarly, but with a twist that defies imagination. Everything in the universe is always moving through spacetime at exactly the same total speed. Always. That speed is the speed of light. You, right now, sitting still, are moving through spacetime at light speed. But here's the key: that motion is divided between movement through space and movement through time. If you're sitting still in space, all your motion is through time. You're moving forward through time at the maximum rate. But if you start moving through space, some of your motion through spacetime gets redirected into spatial motion. And here's the kicker: the faster you move through space, the slower you move through time. This isn't a theory. This isn't speculation. This is observed, measured, confirmed reality. Atomic clocks flown on airplanes tick at different rates than identical clocks left on the ground. Particles created in particle accelerators, moving at tremendous speeds, decay more slowly than they should because time itself is passing more slowly for them. GPS satellites have to account for these time differences, or they'd give you directions that would be off by miles. Time dilation is real. So what happens as you go faster and faster? As you accelerate, as you pour more and more energy into going faster through space, you're actually redirecting more and more of your motion through spacetime from the time direction into the space direction. Time slows down for you. From your perspective, the universe outside starts moving in fast forward. But there's a limit. You can't redirect all your motion into space because you're always moving through spacetime at light speed total. You can asymptotically approach the point where all your motion is through space and none through time, but you can never quite reach it. This is the first barrier, the first hint that light speed is special. As you approach light speed, time slows down for you. At exactly light speed, time would stop. You would experience no time at all. The journey from here to anywhere in the universe would seem instantaneous to you. But this is impossible for anything with mass, anything physical, anything real. Only light itself, which has no mass, can move at light speed. And from light's perspective, if we can even speak of such a thing, there is no journey. The moment a photon is emitted and the moment it is absorbed are the same instant. Light doesn't experience time. But time dilation is just the beginning, just the first sign that something profound is happening. There's something else, something even stranger. As you accelerate, as you approach light speed, space itself changes. Distances contract. The universe shrinks in the direction you're moving. Picture yourself on a spacecraft accelerating toward a distant star. To someone watching from Earth, you appear to be moving faster and faster, but also getting shorter and shorter in your direction of motion. The faster you go, the more compressed you become, like a pancake being squeezed flatter and flatter. At light speed, you would be infinitely compressed, reduced to zero thickness. Of course, this is impossible. You can't actually be compressed to nothing. The universe won't allow it. But here's where things get truly strange, truly alien to our everyday understanding. To you, inside the spacecraft, you don't feel compressed at all. You feel perfectly normal. But the space outside, the distance to your destination, appears to shrink. The faster you go, the closer your destination appears to get. At light speed, if you could reach it, the distance would contract to zero. The entire universe in your direction of travel would be compressed to a single point. Do you see what's happening? The universe is conspiring, at a fundamental level, to prevent you from reaching light speed. Time dilation and length contraction aren't just interesting side effects. They're the universe's way of enforcing a cosmic speed limit. As you go faster, the universe transforms itself in exactly the ways needed to ensure that you can never quite reach that forbidden velocity. But wait. It gets worse. So much worse. Because even if you could somehow overcome time dilation and length contraction, even if the universe cooperated, there's another barrier. A barrier not of time or space but of energy. And this barrier is absolutely, utterly, completely insurmountable. Remember Newton's laws. Force equals mass times acceleration. Apply a force to an object, and it accelerates. Double the force, double the acceleration. Simple. Clean. Wrong. In Einstein's universe, mass isn't constant. As you accelerate, as you approach light speed, your mass increases. The faster you go, the heavier you become. Not because you're gaining matter, but because the energy you're putting into acceleration is being converted into mass. Energy and mass are equivalent, two sides of the same coin. That's what Einstein's most famous equation tells us: energy equals mass times the speed of light squared. Now think about what this means for acceleration. You start with a spacecraft that has a certain mass. You fire your engines, applying force, and you accelerate. Good so far. But as you speed up, your mass increases. Not much at first. At everyday speeds, the increase is negligible, unmeasurable. But as you approach a significant fraction of light speed, your mass starts climbing noticeably. And as your mass increases, the same force produces less acceleration. You need more and more force to achieve the same change in velocity. This creates a vicious cycle, a cosmic trap. The faster you want to go, the more massive you become. The more massive you become, the more force you need to accelerate. The more energy you pump into acceleration, the more your mass increases. It's like running on a treadmill that speeds up the faster you run. You can pour more and more energy into going faster, but most of that energy just gets converted into increased mass rather than increased velocity. Here's the mathematical reality, stark and unforgiving: as you approach light speed, your mass approaches infinity. To actually reach light speed, your mass would have to become infinite. And to accelerate an infinite mass would require infinite energy. Not a lot of energy. Not more energy than exists in all the stars in the galaxy. Infinite energy. Literally infinite. More energy than exists in the entire universe. More energy than could possibly exist under any circumstances. This isn't an engineering problem. This isn't something we can solve with better technology or more advanced science. This is a fundamental property of reality itself. The universe categorically forbids anything with mass from reaching light speed. It's not difficult. It's not extremely challenging. It's impossible in the same way that 2 + 2 = 5 is impossible. The mathematics of the universe simply doesn't allow it. Let's make this concrete. Imagine you have a spacecraft that weighs 100,000 kilograms, about the mass of a large satellite. You want to accelerate it to 90% of light speed. How much energy would that take? The calculation is straightforward, and the answer is staggering: roughly 900,000 trillion joules of energy. That's about 20 times the total annual energy consumption of the entire human civilization. Just to reach 90% of light speed. Now you want to go faster. You want to reach 99% of light speed. The energy required jumps to about 6 million trillion joules. 40 times more energy than before, just to gain an additional 9% of light speed. Your spacecraft, from an external perspective, is now 7 times more massive than when it started, all that additional mass coming from the kinetic energy of motion itself. Keep going. 99.9% of light speed. 60 million trillion joules. Your effective mass is now 22 times your rest mass. 99.99%. 200 million trillion joules. 70 times more massive. Do you see the pattern? Do you see how the energy requirement explodes exponentially as you approach light speed? Every tiny increment closer to that cosmic limit requires exponentially more energy. At 99.9999% of light speed, you'd need energy equivalent to the total mass of several stars, all converted perfectly into kinetic energy. And you still wouldn't be at light speed. You'd still be a tiny fraction away. To close that final gap, to reach actual light speed, you would need infinite energy. The universe draws an asymptotic line that can be approached but never crossed. But let's imagine, just for a moment, that you solved the energy problem. Let's engage in pure fantasy and suppose you discovered some magical source of unlimited energy, Some way to circumvent the mass-energy relationship. You're in your spacecraft, approaching light speed, energy pouring in from your impossible engine. What would happen? Well, the universe would fight you in other ways. At tremendous velocities, even the sparse atoms of interstellar space become a problem. Not just a problem. A catastrophic, apocalyptic threat. At 99% of light speed, every hydrogen atom you encounter, every single solitary atom drifting through the void, hits you with the energy of a bullet. The thin interstellar medium, that near-perfect vacuum that seems so empty and harmless, becomes a hurricane of cosmic radiation. Each atom collision releases enough energy to ionize thousands of other atoms. Your spacecraft would be bathed in a continuous storm of deadly radiation. Go faster, and it gets worse. Much worse. At 99.9% of light speed, those hydrogen atoms hit with the energy of artillery shells. At 99.99%, each atom carries the energy of a small bomb. The cosmic microwave background radiation, that faint echo of the Big Bang that permeates all of space, would be blue-shifted into deadly gamma rays. The universe itself would become a furnace trying to incinerate you. You would need shielding. Massive amounts of shielding. But shielding has mass, and mass is exactly what you're trying to avoid because it makes acceleration even harder. You're caught in another impossible trap. The faster you want to go, the more protection you need. The more protection you need, the more mass you have. The more mass you have, the harder it is to go fast. There's no way out. And there's more. Always more. At these speeds, your spacecraft becomes a relativistic weapon. The kinetic energy you carry is staggering beyond comprehension. If you were to hit anything at all, even a small rock, even a grain of dust, the collision would release energy equivalent to multiple nuclear weapons. You would be annihilated instantly. The debris from your destruction would continue forward, carrying enough energy to potentially sterilize any planets unfortunate enough to be in the path. Some scientists have calculated that a spacecraft moving at 99% of light speed and weighing just 1 kilogram would, upon collision with a stationary object, release energy equivalent to several times the atomic bomb dropped on Hiroshima. Now scale that up to a spacecraft weighing thousands or millions of kilograms. The destructive potential is almost unimaginable. You wouldn't be exploring the galaxy. You would be an existential threat to it. Think about navigation at these speeds. At 99% of light speed, you're covering about 300 million meters every second. The distance from Earth to the Moon would flash by in slightly more than 1 second. You would cross the entire solar system in hours. But how do you navigate? How do you avoid obstacles? How do you detect a piece of space debris in your path when you're moving so fast that even light doesn't give you much warning time? Light from an object ahead of you would reach you only marginally before you reach the object itself because you're moving almost as fast as the light. If something appeared in your path 1 light second away, you'd have barely a second to react. But you can't react that fast. No human can. No computer can issue commands and fire thrusters and change course in 1 second. And even if you could, the energy required to change direction at these velocities would be enormous. You can't just turn. Momentum doesn't care about your desire to avoid collision. So you're trapped moving in a straight line, unable to deviate, unable to stop, a relativistic bullet hurtling through space with no way to control your trajectory. This isn't travel. This is a cosmic death wish. You would need to know, with absolute certainty, that your entire path was completely clear of any debris, any rocks, any dust, anything at all. For distances of light years. The slightest error in calculation, the smallest unknown object, would mean instant annihilation. But perhaps, you might think, we don't need to carry fuel. Perhaps we could use some kind of ramjet, scooping up hydrogen from interstellar space and using it as fuel. This idea has been proposed, studied, analyzed. It sounds clever. Use the medium through which you're traveling as your fuel source. No need to carry enormous fuel tanks. Just scoop and burn. Except the physics don't work. At the speeds where a ramjet might be useful, those same hydrogen atoms that you're trying to scoop up are hitting you with incredible force, creating drag. You're trying to gather fuel from a stream that's simultaneously sandblasting your spacecraft to pieces. The energy you gain from the fuel is less than the energy you lose to drag and radiation. You go slower, not faster. The ramjet becomes a ram brake, decelerating you despite your best efforts. And what about propulsion itself? Set aside the energy requirements for a moment. How do you actually accelerate something to near light speed? Rockets? Conventional rockets are impossibly inefficient. The tyranny of the rocket equation means that to accelerate a payload to high velocities, you need exponentially more fuel. To reach even a tiny fraction of light speed with chemical rockets would require a fuel tank larger than planets. Literally. The numbers simply don't work. Ion drives? Better, more efficient, but still nowhere near what you need. Nuclear propulsion? Fusion drives? Even if we could build perfect fusion engines, engines that convert mass to energy with 100% efficiency, the energy requirements for near light speed travel would require fuel masses comparable to your spacecraft's mass. You'd be back in the same trap: more fuel means more mass means more energy needed means more fuel. What about antimatter? The ultimate fuel, with the highest energy density physically possible. When matter and antimatter meet, they annihilate completely, converting all their mass into pure energy with perfect efficiency. Surely antimatter is the answer. Except producing antimatter requires energy, lots of energy, far more energy than you get back when you use it. Creating antimatter is incredibly difficult and expensive. The entire supply of antimatter ever created by humanity could light a light bulb for a few minutes. Producing enough antimatter to fuel an interstellar journey would require energy output equivalent to all the power humanity has ever generated throughout our entire history. Multiplied by millions. And even if you somehow solved that problem, even if you had unlimited antimatter, you'd still face the fundamental relativistic mass increase. You'd still need infinite energy to reach light speed. Antimatter doesn't magically bypass the laws of physics. It's just a very efficient energy storage mechanism. But efficiency doesn't matter when you need literally infinite energy. Perhaps you're thinking about other alternatives, exotic ideas from the fringes of physics. What about solar sails, pushed by lasers from home? What about nuclear pulse propulsion, riding explosions? What about quantum vacuum drives or warp bubbles or manipulation of spacetime itself? Surely somewhere in our advanced understanding of physics, there's a loophole, a way around these barriers. Let's examine these ideas one by one, because they're fascinating, because they represent humanity's refusal to accept limits, our desperate need to find a way forward even when the universe seems to be saying no. Solar sails, for instance. The concept is beautiful. A spacecraft with a gigantic mirror-like sail, reflecting photons from a powerful laser back on Earth. The pressure of light itself provides thrust. No fuel needed. Just light. This could work, in principle, for reaching significant fractions of light speed. Maybe 10%, maybe 20% if you built enormous lasers and enormous sails. But there are problems. Huge problems. First, the sail has to be incredibly light and incredibly strong. Strong enough to withstand the intense pressure of the laser without tearing, light enough that the pressure of light can actually accelerate it. We're talking about materials that barely exist even in theory. Second, the laser has to be phenomenally powerful. Powerful enough to push a spacecraft over interstellar distances. Powerful enough that the beam doesn't spread and diffuse as it travels across light years of space. We're talking about power outputs that dwarf anything humanity can currently produce. We're talking about constructs that might require the resources of an entire solar system to build. Third, and this is crucial, a solar sail can only accelerate. It can't slow down once it reaches its destination because the laser is back at Earth, pushing you away from home. You'd have to build another laser at your destination to slow you down. But your destination is an alien star system where no one has ever been. How do you build the laser there? You'd have to send something ahead to build it, but that something would face the exact same problem, no way to slow down. You could use the destination star's light to slow down, but stars are much less intense than focused lasers. Your deceleration would be far slower than your acceleration. You might spend centuries decelerating, drifting through the star system at tremendous speed, unable to stop at the planets you came to explore. Or you could try gravity assists, slingshotting around the star to slow down, but that's incredibly difficult to calculate and execute precisely, especially when you're moving at relativistic speeds. Nuclear pulse propulsion is another idea that sounds promising. Explode nuclear bombs behind your spacecraft, ride the shockwave, use the explosion's energy to push you forward. This actually could work for reaching maybe 5 or 10% of light speed. But you'd need thousands or millions of nuclear weapons. You'd need to set them off in rapid succession. The engineering challenges are staggering. The political and ethical challenges might be even worse. Do we really want to detonate thousands of nuclear weapons in space, littering the solar system with radioactive debris? And again, even if you solved all these problems, 5 or 10% of light speed is still just a tiny fraction of what light itself achieves. The nearest star system is over 4 light-years away. At 10% of light speed, that's a 40-year journey. You'd need life support for 4 decades. You'd need to protect against cosmic radiation for 4 decades. Your crew would age 40 years during the journey. And that's to reach our closest stellar neighbor. To reach anything interesting, any star system with planets that might harbor life, you'd need to travel hundreds or thousands of light-years. At 10% of light speed, that's millennia. Civilizations rise and fall faster than that. So we keep searching for alternatives. Warp drives. This is the favorite of science fiction, the staple of countless stories. Don't move through space at all. Instead, contract space in front of you and expand space behind you. Create a bubble of warped spacetime that carries you along, surfing on a wave of distorted reality. Inside the bubble, you're not moving at all relative to your local space. The space itself is moving. This supposedly bypasses the light speed limit because you're not actually accelerating to light speed. You're just riding along while space does the moving for you. It's a beautiful idea. Elegant. Tempting. And based on real physics. The equations of general relativity do indeed allow for solutions where spacetime itself moves. Warp drives are mathematically possible. But, and this is an enormous but, they require something that probably doesn't exist, exotic matter with negative energy density. What does that even mean? Normal matter and normal energy have positive energy density. They make spacetime curve in specific ways, creating gravity that pulls things together. But to create a warp bubble, you need matter or energy that curves spacetime the opposite way, that pushes instead of pulls. You need negative energy. And we've never seen such a thing. Never detected it. Never created it. It might not exist at all in our universe. Some physicists have speculated about quantum effects that could, under extremely specific circumstances, create tiny regions of negative energy. But we're talking about effects so small, so fleeting, so difficult to harness that calling them impractical is a laughable understatement. To create a warp bubble large enough to contain a spacecraft would require amounts of negative energy that might exceed all the positive energy in the observable universe. We're not talking about difficult engineering. We're talking about physics that might be fundamentally impossible. And even if you could create a warp bubble, even if negative energy exists and can be harnessed, there are other problems. What happens to any normal matter that enters the bubble? What happens to the light and particles you encounter along the way? Some calculations suggest they'd accumulate at the front of the bubble, building up a deadly bow wave of radiation. When you turned off the warp drive, all that accumulated energy might be released forward in a catastrophic burst that would sterilize everything in front of you. Your arrival at a new star system would be announced by a blast of radiation intense enough to scour planets clean of life. Other calculations suggest that creating and maintaining a warp bubble might require you to move faster than light relative to your starting point to even set up the necessary spacetime configuration. Which creates a causality paradox. You need to already be going faster than light in order to create the conditions that would let you go faster than light. It's like needing to already be on the other side of a door to unlock the door. The logic eats itself. Wormholes, then. Another favorite of science fiction. A tunnel through spacetime, connecting two distant points. Step into one end, step out the other, potentially light years away. Distance becomes meaningless. You're not traveling through space. You're bypassing space entirely, taking a shortcut through higher dimensions. Again, the mathematics allows this. Einstein's equations don't forbid wormholes. But, and here's that word again, they require exotic conditions to exist. First, you need either exotic matter with negative energy to keep the wormhole open, or you need it to have existed naturally since the Big Bang. Natural wormholes, if they ever existed, would be microscopic and would probably collapse instantly. You can't travel through something smaller than an atom that exists for a tiny fraction of a second. Could you enlarge a wormhole? Could you stabilize it? The energy requirements are, once again, astronomical. Possibly infinite. Possibly impossible. And that's assuming you can find one in the first place. Where do you even look? How would you detect something like this? A wormhole, if it existed, would be incredibly difficult to observe. It might look like a gravitational lens, might distort light in specific ways, but so do many other astronomical objects. And let's say you somehow found one, enlarged it, stabilized it. You have another problem, causality. A wormhole could potentially be used as a time machine. By manipulating the two ends of the wormhole, moving one relative to the other at high speeds, you could create a situation where entering one end takes you back in time relative to the other end. Time travel creates paradoxes, causality violations, situations where effects precede causes. The universe might not allow this. Some physicists have proposed that quantum effects would conspire to destroy any wormhole the moment it could be used for time travel. Reality protecting itself from paradox. Every solution we propose runs into walls. Hard walls. Walls built from the fundamental laws of physics. We can't accelerate to light speed because mass increases require infinite energy. We can't use warp drives because they require physics that might not exist. We can't use wormholes because they're unstable and might violate causality. We can't use any of the clever tricks we can imagine because the universe has thought of them first and closed the loopholes. It's frustrating. Maddening. We can see the stars. We can calculate the distances. We can imagine what might be out there. But we can't reach it. We're trapped, confined to our little corner of space by physics that doesn't care about our dreams or ambitions. The speed of light isn't just a speed limit. It's a prison wall. But why? Why would the universe be constructed this way? Why would reality have this fundamental limitation built into its very core? Is it arbitrary? Is it some cosmic accident? Or is there a reason, a deeper logic to why nothing with mass can reach light speed? Consider what light speed represents. It's not really about light. Light just happens to move at this speed because photons have no mass. But the speed itself, that value of roughly 300 million meters per second, is fundamental. It's the speed at which causality propagates through the universe. It's the speed at which information can travel. It's the speed at which cause and effect can connect. In Einstein's universe, spacetime is a unified four-dimensional structure. Events in this structure are connected by light cones. Everything that could have affected an event lies inside its past light cone. Everything the event could affect lies inside its future light cone. These light cones are defined by, you guessed it, the speed of light. If you could go faster than light, you could move outside these light cones. You could affect events that couldn't have affected you. You could receive effects from events you couldn't have caused. Causality would break down. Imagine being able to send a signal faster than light. You send a message to a distant star. But because of the relativity of simultaneity, another observer moving relative to you might see your message arrive before you sent it. From their perspective, the effect precedes the cause. Information would flow backward in time. This opens up all sorts of paradoxes. Could you send yourself a message telling you not to send the message? Could you prevent your own past actions? The logic becomes incoherent. The universe seems to be constructed to prevent these sorts of paradoxes. Light speed isn't arbitrary. It's the speed at which causality itself operates. Going faster than light would mean breaking causality, creating a universe where effects could precede causes, where time's arrow could point in multiple directions, where logic itself might cease to function. The universe doesn't allow this. Can't allow this. The very structure of reality depends on this limit. So the speed of light is really the speed of causality, the speed of information, the speed at which the universe updates itself. And this speed is absolute, invariant, the same for all observers. This is what makes spacetime work. This is what makes reality coherent. Without this limit, without this cosmic speed restriction, the universe as we know it couldn't exist. Physics would collapse into paradox and contradiction. From this perspective, the light speed limit isn't a barrier placed in our way to frustrate our ambitions. It's a foundational principle that makes existence itself possible. We're not being kept from the stars by an arbitrary rule. We're being kept from the stars by the same logic that allows stars to exist in the first place, that allows causality to function, that allows time to have meaning. Does this make it less frustrating? Not really. We still gaze up at the night sky and yearn to explore what we see. We still dream of touching alien worlds, of meeting alien minds, of spreading consciousness throughout the cosmos. And we still face the cold, hard reality that the physics of the universe makes this dream almost impossibly difficult to achieve. Notice that word, almost. Because while we can't reach light speed, we can potentially reach significant fractions of it. We could, in principle, build spacecraft that travel at 10%, 20%, maybe even 50% of light speed. It would require technologies we don't yet have, energy sources we haven't yet mastered, resources on a scale we haven't yet achieved. But it's not impossible. Not fundamentally forbidden by physics. Just extremely, monumentally difficult. At half-light speed, the nearest star system is 8 years away. Still a long journey, but within the span of a human lifetime. You could conceivably send a crew on such a mission and have them return, aged but alive, to tell us what they found. At 20% of light speed. Many nearby stars become accessible within a few decades. We could send out probes, robotic explorers, seeds of human civilization to establish outposts on distant worlds. This is still interstellar travel, still exploration of the galaxy. Just slower than we might wish. Just harder than science fiction made us believe. The stars are not forever out of reach. They're just very, very far away, and reaching them will require patience, resources, and determination on a scale humanity has never before attempted. But here's the thing. Here's the realization that both humbles us and gives us hope. The universe is old. Incredibly old. 13.8 billion years since the Big Bang. Our Sun is only 4.6 billion years old, relatively young in cosmic terms. There are stars in our galaxy that formed when the universe was barely a billion years old. There could be civilizations out there that have existed for billions of years longer than ours has. If interstellar travel is limited to subliminal speeds, if every technological civilization faces the same barriers we do, then perhaps the galaxy is quiet not because no one else exists, but because everyone else is facing the same fundamental limitations. Perhaps advanced civilizations don't spread across the galaxy in a wave of colonization because doing so is simply too slow, too difficult, too resource-intensive to be practical. Or perhaps they've adapted. Perhaps they've accepted that exploration and colonization on galactic scales takes not centuries or millennia, but millions of years. Perhaps they send out robotic probes that travel for tens of thousands of years between stars, slowly, patiently mapping and exploring. Perhaps they've given up on the idea of a unified galactic empire and instead focus on their home systems, building Dyson spheres and stellar habitats, reshaping their local space into gardens of unimaginable complexity. Perhaps the light speed limit is a great filter, a challenge that every spacefaring civilization must confront. Some might give up, deciding that the stars are simply too far away to bother with. Others might persevere, sending generation ships on journeys that last longer than most civilizations survive. Still others might find alternative approaches we haven't yet imagined, ways to explore and communicate and grow that don't require physical presence. And there's another possibility, one that's both melancholy and beautiful. Perhaps the light speed limit isn't a barrier to exploration but a protection. Perhaps it ensures that life, when it arises, has time and space to develop independently. Without faster-than-light travel, there can be no galactic empires. No civilization can spread so fast that it homogenizes the entire galaxy. Each world where life emerges has millions or billions of years to evolve its own solutions, its own forms, its own consciousness, without interference. The speed of light, from this view, creates diversity. It ensures that the universe is full of unique, independent developments. It prevents any single form of life from dominating everything. It makes the cosmos richer, more varied, more interesting. If we could travel at light speed, we might spread so quickly that we'd fill the galaxy before other forms of life had time to emerge and develop. The light speed limit might be the universe's way of ensuring that consciousness, wherever it arises, has its own space to grow. This is, of course, speculation. Philosophy dressed up as physics. We don't know why the universe is structured the way it is. We don't know if there are other universes with different physical constants, different speeds of light, different rules. We only know our universe, and in our universe, light speed is the limit. This is simply a fact we must accept and work within. But accepting a limitation doesn't mean giving up. Throughout history, humans have faced seemingly insurmountable barriers and found ways around them, through them, over them. We couldn't fly until we understood aerodynamics. We couldn't split atoms until we understood quantum mechanics. We couldn't reach space until we understood orbital mechanics and rocket science. Each time, we didn't break the laws of physics. We learned them more deeply and used that knowledge to do what had seemed impossible. So perhaps there's something we're missing. Perhaps our understanding of physics, despite all its successes, is still incomplete. After all, we know there are gaps in our knowledge. We don't understand dark matter or dark energy, which together make up 95% of the universe's mass energy content. We haven't unified quantum mechanics and general relativity. We don't fully understand the nature of time or the origin of the universe's physical constants. There's so much we still don't know. Could there be something in that unknown territory, some deeper understanding of physics that would give us options we haven't yet imagined? Could quantum mechanics, which already routinely violates our intuitions about reality, hold some key we haven't yet turned? Could the strange properties of black holes or the exotic physics of the early universe or the mysterious nature of dark energy offer a loophole? Maybe. But probably not. Because while our understanding of physics is incomplete, it's not wrong. Einstein's relativity has been tested thousands of times in thousands of ways, and it's never failed. Every prediction has been confirmed. Every strange implication has been verified. Black holes exist. Gravitational waves exist. Time dilation is real. Space contraction is real. Mass energy equivalence is real. The speed of light as a universal constant is real. This isn't speculation or theory in the colloquial sense. This is tested, verified, confirmed reality. So if there is a way around the light speed limit, it would have to come from physics we don't yet know, physics beyond Einstein. But that new physics would have to reduce to Einstein's physics in all the cases we've already tested, which is a lot of cases. It would have to be compatible with everything we already know while somehow opening up new possibilities. That's a very tall order. Not impossible, but not likely either. And even if we found such a loophole, who's to say it would be usable? Quantum mechanics allows for quantum tunneling, where particles can appear on the other side of barriers they shouldn't be able to cross. But this doesn't mean you can tunnel yourself through walls. The probability of all the particles in your body simultaneously tunneling in the same direction is so absurdly small that it would never happen even if you waited longer than the current age of the universe. Some things are technically possible but practically impossible. So we're back where we started. Limited. Confined. Unable to reach the one speed that would truly liberate us to explore the cosmos. The speed of light remains forever tantalizingly out of reach, not because we're not clever enough, not because we haven't tried hard enough, but because the universe itself forbids it. The mathematics is clear. The physics is unambiguous. Light speed is the cosmic speed limit, and nothing with mass can reach it. And yet we keep looking up. We keep dreaming. We keep imagining ourselves among the stars. Why? Why do we persist in dreaming of what we cannot have? Why does the impossibility of light speed travel not crush our spirit of exploration? Perhaps because deep down, we understand that the journey is more important than the destination. Perhaps because the challenge itself is what makes us human. We've always reached for what seemed impossible. We've always pushed against our limitations. Sometimes we succeed. Sometimes we fail. But we always try. That's our nature. That's what defines us as a species. The speed of light tells us we can't have easy answers, quick solutions, magical shortcuts. It tells us that the universe is vast beyond comprehension and that truly exploring it will require patience and persistence and commitment on scales we've never before attempted. It tells us that if we want to reach the stars, we'll have to earn it. We'll have to develop technologies and societies and strategies that can sustain themselves across centuries or millennia. This is daunting. Terrifying even. But also, in a strange way, it's liberating. Because if there are no shortcuts, if there are no easy paths, then the playing field is level. Any civilization that wants to explore the galaxy faces the same challenges we do. Intelligence and creativity and determination matter more than luck or circumstance. We're not disadvantaged by living in this particular part of space or in this particular time. We face the same fundamental physics as everyone else. And perhaps that's the deepest lesson of the light speed limit. Perhaps it's teaching us that the universe doesn't owe us anything. It doesn't care about our dreams or desires. It operates according to laws that existed long before we did and will continue long after we're gone. We're not special. We're not chosen. We're just one more species on one more planet orbiting one more star in a galaxy of hundreds of billions of stars. But we're also conscious. We're aware. We can understand these laws even if we can't break them. We can look at the equations that govern reality and comprehend what they mean. We can stare into the face of cosmic limitations and refuse to despair. We can accept that we'll never travel at light speed while simultaneously refusing to accept that this makes exploration impossible. There's a strange dignity in this. A quiet heroism in acknowledging limits while pushing against them anyway. We're finite beings in an infinite universe, brief flickers of consciousness in the vast darkness. The light speed barrier reminds us of our limitations, our mortality, our smallness. But it doesn't diminish us. If anything, it makes our dreams more precious because we dream them knowing how hard they'll be to achieve. Think about it. If light speed travel were easy, if we could just build a ship and zoom off to distant galaxies, what would that mean? It would mean the universe was simple, accessible, easily conquered. It would mean there was no real challenge, no genuine obstacle to overcome. We could spread across the stars like tourists at an amusement park, visiting one attraction after another without effort or sacrifice. But that's not the universe we live in. We live in a universe that demands everything from us. That requires us to be clever and resourceful and determined. That forces us to cooperate on scales beyond anything we've achieved. That asks us to think not in terms of years or decades but in terms of centuries and millennia. That challenges us to become worthy of the stars before we can reach them. The light speed limit is the universe asking us a question: how badly do you want this? Are you willing to commit the resources? Are you willing to develop the technologies? Are you willing to build the societies that could sustain a multi-generational journey to another star? Are you willing to bet your civilization's future on a dream that won't be fulfilled in your lifetime, or your children's lifetimes, or their children's lifetimes? Most species, if we're honest, would probably say no. The challenges are too great. The timescales are too long. The uncertainties are too vast. It's easier to stay home, to focus on local problems, to live within the comfortable boundaries of your home world. And there's nothing wrong with that choice. Civilizations don't have to explore the stars to be worthwhile or meaningful. A civilization that creates art and music and literature and philosophy, that solves the problems of disease and poverty and suffering, that builds a sustainable relationship with its environment, that gives its members meaningful lives, such a civilization has achieved something remarkable even if it never leaves its home system. But if we do choose to reach for the stars, if we decide that despite the obstacles and the limitations and the physics that says light speed is forever out of reach, we're going to try anyway, then we're committing to something extraordinary. We're saying that we value exploration and discovery and growth so much that we're willing to work for generations toward goals we'll never personally see achieved. We're saying that we're more than just individuals trying to maximize our own happiness. We're part of something larger, something that extends beyond our own lifetimes. This is what the light speed limit ultimately teaches us. Not that we're weak or limited or trapped. But that anything truly worthwhile requires sacrifice, commitment, vision. The easy paths aren't worth taking. The impossible dreams are the only ones worth chasing. And even though we can never reach light speed, even though the universe has drawn a line we cannot cross, we can still accomplish incredible things within those constraints. Because here's a secret that the physics doesn't immediately reveal. While light speed is the ultimate limit, we don't need to reach it to explore the galaxy. Thanks to time dilation, thanks to the weird properties of spacetime, a journey that takes thousands of years from Earth's perspective might take far less time from the perspective of the travelers. At 99.9% of light speed, time slows down so much that you could cross the entire galaxy, 100,000 light-years, in just a few decades of subjective time. You'd return to find that 100,000 years had passed on Earth, that everyone you knew was long dead, that human civilization had risen and fallen and risen again, that the Earth itself might be unrecognizable. You couldn't go home, not really, not to the home you left. But you could explore. You could see things no one from your time ever saw. You could witness the birth of stars and the death of galaxies. You could potentially outlive your entire civilization while still being young yourself. This is the trade-off the universe offers. You can't go fast from anyone else's perspective. But you can, in a sense, cheat time from your own perspective. The journey to distant stars doesn't have to take your whole life, even if it takes multiple lifetimes back home. This doesn't solve all the problems. It doesn't make interstellar colonization easy. But it means that exploration, at least, is possible. We can send people to other stars, and those people can actually experience the journey and arrive at their destination while still alive. Of course, this creates its own challenges. How do you say goodbye to everyone you love, knowing you'll never see them again? How do you cope with the knowledge that you're traveling not just through space but through time, leaving behind everything familiar? How does society handle the fact that explorers who leave might return to a world that's moved on without them, where they're anachronisms, relics from a forgotten age? These are psychological and social challenges, not physical ones. But they're no less real for that. Interstellar travel isn't just an engineering problem. It's a human problem. It requires us to rethink our relationships, our sense of belonging, our connection to place and time. It requires us to develop new frameworks for thinking about identity and community and home. And maybe that's okay. Maybe that's part of the growth we need to experience. Maybe confronting these challenges is part of becoming a spacefaring civilization. Maybe the light speed limit, by making interstellar travel so difficult, forces us to evolve in ways we wouldn't otherwise. Forces us to think bigger, plan longer, cooperate more fully. Forces us to become better than we are. There's a perspective from which the light speed limit is a gift rather than a curse. It prevents us from spreading thoughtlessly across the galaxy. It ensures that any expansion we do undertake is deliberate, planned, considered. It protects us from our own impulsiveness. It gives us time to mature as a species before we encounter other forms of life or spread our influence beyond our home system. Imagine if we could travel at light speed right now, with our current level of technological and social development. We'd probably make terrible mistakes. We'd likely bring our conflicts and prejudices and short-sighted thinking to every new world we reached. We might do irreparable harm to alien ecosystems or even alien civilizations. We'd be children with godlike power, dangerous to ourselves and others. But if reaching the stars requires centuries of development, requires us to solve our energy problems and our resource problems and our social problems, requires us to build a civilization that can think and plan on multi-generational timescales, then by the time we actually achieve interstellar travel, we might be wise enough to do it responsibly. We might have outgrown our adolescent phase as a species. We might be ready, truly ready, to be ambassadors to the cosmos rather than conquerors. This is speculative, of course. We don't know how humanity will develop. We don't know if we'll solve our problems or succumb to them. We don't know if we'll ever achieve interstellar travel at all, whether at light speed or far below it. The future is open, undetermined, full of possibilities both wonderful and terrible. But the light speed limit is a constant. It's one of the few certainties we have about the future. Whatever else changes, whatever technologies we develop, whatever discoveries we make, we will never travel at light speed. This limit will always be there, defining what's possible, constraining our options, shaping our destiny. And somehow, knowing this, accepting this, we still look up at the stars and dream. We still imagine ourselves out there, exploring, discovering, growing. We still tell stories about starships and alien worlds and adventures in the depths of space. We still believe, despite everything, that the stars are for us. Maybe we're foolish. Maybe we're in denial. Maybe we're refusing to accept an obvious truth. Or maybe we understand something deeper. Maybe we know that limitations don't define us. Maybe we recognize that the human spirit has always found ways to transcend its boundaries, not by breaking physical laws but by reinterpreting what's possible within them. We couldn't fly until we understood that we didn't need to flap our wings like birds. We couldn't reach the moon until we understood that we didn't need a ladder from Earth. We won't reach the stars by traveling at light speed because we can't. But we might reach them anyway, by traveling at 90% of light speed, or 50%, or 20%. By building generation ships. By developing suspended animation. By sending our minds instead of our bodies. By creating artificial intelligence that can explore on our behalf. By methods we haven't yet imagined because we haven't yet needed to imagine them. The history of human achievement is a history of doing impossible things. Not by ignoring reality, but by understanding it so deeply that we find possibilities no one else saw. The light speed limit seems absolute, and it is absolute in the sense that we can't exceed it. But maybe it's not absolute in the sense that it prevents us from reaching the stars. Maybe it just means we have to be more creative, more patient, more committed than we thought. And if we fail, if it turns out that interstellar travel is simply too difficult even at subliminal speeds, if the distances are too vast and the energies required are too great and the time scales are too long, what then? Will we have wasted our efforts? Will we have pursued a dream that was always hopeless? No. Because the pursuit itself changes us. The attempt to reach the stars forces us to develop technologies that can help us here at home. It requires us to think about energy and propulsion and life support in new ways. It demands that we cooperate internationally, plan for the long term, consider the welfare of future generations. These are all things that make us better, whether or not we ever leave the solar system. And there's something to be said for having dreams that transcend us, goals that won't be achieved in our lifetimes. It gives us perspective. It reminds us that we're part of something larger than ourselves, that our actions have consequences that will ripple forward through time. It helps us think beyond the immediate, beyond the next quarter or the next election or the next crisis. It gives us purpose. So maybe the light speed limit is teaching us the most important lesson of all, that the destination isn't the point. The journey is the point. The striving is the point. The refusal to accept that anything worthwhile should come easy is the point. We reach for the stars not because we're certain we'll succeed, but because the reaching itself makes us more than we were. This is the paradox at the heart of the light speed barrier. It's an absolute limit that we cannot exceed. But it's also a challenge that we cannot ignore. It tells us that we're small and limited and finite. But it also tells us that we're capable of understanding our limits, of accepting them while simultaneously refusing to be defined by them. We're the species that looks at the impossible and says, okay, but let's try anyway. And maybe that's enough. Maybe that's all we need to be. Not the species that travels at light speed, but the species that dares to dream of it. Not the civilization that conquers the galaxy, but the civilization that reaches toward it with trembling hands and hopeful hearts. Not the masters of the universe, but the explorers of it, humble and determined and endlessly curious. The speed of light will never be ours. The equations are clear. The physics is unambiguous. We will never travel that fast. But we can travel. We can explore. We can reach beyond our world and touch other worlds. We can send our minds and our machines and maybe even ourselves to places no human has ever been. We can grow and learn and discover. We can become more than we are. And in the end, perhaps that's what the light speed limit is really about. Not what we can't do, but what we can. Not the doors that are closed to us, but the ones that remain open. Not the final barrier, but the first step on a journey that will define us as a species for as long as we exist. We will never travel at light speed. This is a fact, unchangeable and eternal. But we will travel. We will reach for the stars. We will dream impossible dreams and pursue them with everything we have. And in that pursuit, in that reaching, in that refusal to be limited by our limitations, we will find what it means to be truly alive. The universe has given us a cosmos to explore and laws that govern how we can explore it. The speed of light is one of those laws, perhaps the most fundamental. It tells us that some things are impossible, that some boundaries cannot be crossed, that some dreams cannot be realized in the way we imagined. But it doesn't tell us to stop dreaming. It doesn't tell us to give up. It doesn't tell us that we're worthless or meaningless because we face limits. If anything, it does the opposite. It tells us that we live in a universe of structure and order, where effects have causes and time has direction and causality has meaning. It tells us that reality is knowable, understandable, predictable. It tells us that while we face constraints, we also face opportunities. We can know the speed of light. We can understand why nothing with mass can reach it. We can work within these constraints to achieve remarkable things. We can't break the laws of physics, but we can use them, work with them, find creative solutions within the boundaries they set. This is what intelligence means. This is what it means to be conscious in a material universe. So we stand here on our small world, looking up at the vast darkness punctuated by distant lights. We understand now, in ways our ancestors never could, just how far away those lights are. We understand the physics that governs them and us. We understand the limitations we face. And we understand that reaching those lights, touching those distant suns, will require more from us than we've ever given before. But we're going to try anyway. Not because it's easy. Not because success is guaranteed. Not because we can ignore the physics. But because trying is what we do. Because reaching is what makes us human. Because the impossible is the only thing worth chasing. We will never travel at light speed. But we will travel. And perhaps that's enough. Perhaps that's everything. Perhaps in accepting what we cannot do while pursuing what we can, we find the truest expression of what it means to be human, to be conscious, to be alive in this strange and beautiful universe that gave us birth and set us dreaming of stars.